Okay, great. So we're running a little late, so let's get started. I'm very happy to have Professor Charles Brown here. Charles hails from Yale, Department of Physics. He was an undergraduate at the University of Minnesota, and then went to Yale for his PhD. Worked in the group of Jack Harris and some really cool experiments, the optical mechanics of liquid helium. And I think if you remember, Jack was out here last year, so somebody might have called some of those experiments. Then after his PhD, he moved to some university across the bay. Bag, I see. I'm giving you a bag. Where we worked with Dan Stamperkern and built up a nice lattice experiment, the Agonate lattices. And last year moved back to Yale, where he has a laboratory, again, exploring some interesting quantum many-body physics, quantum simulation, with atoms and lattices.
All right. Well, thank you, Ben, for the invitation. Thanks, everyone, for being here. So like Ben said, I'm going to tell you about a quantum simulation experiment that I'm building up at Yale right now. So to that end, I'll tell you about a so-called tenfold, should say rotation-symmetric. I just wanted to drop the word rotation just to keep it a little simpler. Quasicrystal quantum simulator. Okay. First, let me acknowledge my team. I work with a team of postdocs and grad students at the moment. Also wanted to acknowledge the people who have been, or institutions, entities that have been supporting our efforts. So that is Yale itself, the Yale Quantum Institute, and most recently AFOSR. Oh, sure, that'd be great. I think it was great.
It's good? Okay.
It was okay with other people.
It'll be so exciting you won't even want to. And it's fun.
Good. So I mentioned quantum simulation. What do I mean by that? I mean the use of a simpler quantum system. That's what I build in my lab, to emulate the behavior of another more complex quantum system. For me, that is recently things like what I would call quantum materials, or maybe topological quantum materials like graphene. Okay, so that's the goal. Do quantum simulation of interesting solid-state materials where the interplay of quantum mechanics and topology leads to exotic macroscopic behavior. Okay. And so when you think of quantum simulation, you can typically think of it in sort of two different ways. That is digital simulation. This will be what's called a universal quantum simulator. This is a proper quantum computer where you're implementing gates and such. Or analog simulation. This is a system that is different from the solid state system. Say my example you want to emulate. You can think of it as sort of a toy model of that solid state system, but one that is much more controllable than a solid state system. So for example, in an optical lattice, this is an optical potential where atoms hopping around like electrons hopping around a solid. We can control defects, we can control size of the system, and so the rate of the dynamics, et cetera. Okay. So when you think of digital and analog simulation, you can realize it in different platforms. I highlighted my favorite one, full atoms and lattices, at least at the moment, it's my favorite one. But also you can do this sort of thing with trapped ion chains or optical tweezer arrays, or even all photonic systems. Okay. So here is a quick picture sort of describing really what I just said. In a solid crystal, in a really simple case, you have an array of positively charged ions, and electrons hop around those ions. And it's the details of that hopping process that determines things like how does this material, of course, conduct electricity or heat, but also how does it behave optically? What's its color? Its transparency. There are more exotic things like magnetism that come into play, where this sort of hopping detail can affect that. Okay. However, for us on the quantum simulation side, instead of an array of charged ions, we have an array of optical maxima. Right? This is my optical lattice. Make this with lasers. And instead of having electrons hopping around this 1D array, you have ultrafold atoms. Okay, and so I liken both of these things two ways, both electrons and ultra-cold atoms. They're both matter waves. At some level, at the end of the day, if you're studying solid materials, simulated solid materials, you're studying details of the propagation of matter waves, charged or neutral, in some background potential that has some set of symmetries. And as usual in physics, the symmetries that are in play are important. Generally, symmetries have a pretty profound impact on the physics that's at play. Okay? And that has a lot of is a large part of the reason why I'm interested in quasicrystals. They have a very different set of symmetries. Okay, so I like to be very pedagogical when I can be. I think this is a good opportunity to be, and I realize the audience has a varied set of experience. So we're going to walk through the sort of set of things you need in order to make an experimental quantum simulator. I'll talk to you about the matter wave part, about the potential part, and then we'll sort of have the tools we need to realize a lattice experiment. Okay, so to start with the atom waves, we start with this. So we want to see wave behavior, which means we need the atoms to be cold. We need to be thinking then about the Broglie lambda dB, which is proportional to 1 over the square root of the temperature. So how cold do you need your system roughly to be, or order of magnitude to be, in order to start seeing wave behavior in atoms, where the Broglie wavelengths start to sort of overlap on a large scale? Something like a microkelvin. This is a little hot, but something like 100 nanokelvin, microkelvin, right, to start seeing this. Okay, and so here's a sort of a large range of temperatures with some nice pictures that sort of just give you a quick glance at how we go from having a relatively hot thermal gas to having a so-called quantum degenerate gas. Okay, so here's a picture from Martin Zerlein's group of sodium. Right, this is a beam of sodium here. Right, it's at 700 Kelvin or so. It shoots through a Zeeman slower into this region called the three-dimensional magneto-optical trap, the MOP, that gets over the course of applying cooling with laser beams and magnetic field over like a meter, you go from 700 Kelvin to roughly a millikelvin. Right now you have a cold thermal cloud, and then through a few different evaporation processes, right? In a way similar to how a cup of coffee evaporatively cooled. You apply evaporation techniques to go from something like a millikelvin to something like less than a microkelvin. And that allows you to undergo a phase transition from classical gas to quantum degenerate gas. Okay. Now, whether that's a bosonic degenerate quantum gas or a DEC, or degenerate Fermi gas, there's some details there, but this is roughly the process. Okay, so of course, photons carry momentum, and so this is a sort of funny thing, I think, for a lot of people who don't do laser cooling via atomic physics. You can shine light on objects, on atoms, in order to cool them. Okay? That is, if you shine light at an atom such that it absorbs momentum that is, let's say, anti-parallel to its velocity, then after lots of momentum kicks, you can sort of decrease its momentum, T squared over 2m, and energy, blah, 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 right? So this is a way to cool atoms. Okay, so I have a cool little animation here for you. You can imagine your atom here with some light counter-propagating. And I don't know if you caught that, it's a little hard to see. Let me actually go back. So here's my electron cloud, this sort of haze around the nucleus. And when my light is resonant with this transition between my ground and excited state, I excite my electron, okay? This gives the atom a momentum kick, right? I can apply forces to the atoms. So then I can control their motion, I can cool them, I can extract energy from them. Okay. So this allows us to do things like make two-dimensional magneto-optical traps. This makes atomic beams, imagine sort of water shooting out of a garden hose, right? That lead into 3D MOPs. Imagine sort of a bowl where I can make a cloud of atoms to, get them to 10 to 100 microkelvin, depending exactly on which alkali atom I'm using. I'm using alkali atoms in recent years. I'll continue to do so. And then you can do fancier sub-Doppler cooling. This GM stands for gray molasses. This is just an additional technique to get the atoms a little colder before you do the actual process that gives you a quantum gas, like a DEC or a degenerate Fermi gas. Okay, so that's how we do the initial cooling. Let me tell you a bit about the atom trapping part. right? So atoms are little dipoles that have some magnetic moment mu. The energy of the dipole in the magnetic field is minus mu dot B. So this is my magnetic trap, my collection of atoms, okay? I can realize a magnetic trap like this using anti-Helmholtz coils, right? So you can have Helmholtz coils or anti-Helmholtz coils depending on the direction of the current. You can have a large solenoidal field that just gives you a large static constant B field, or you can make something where the B field varies linearly in this way about the center of the trap. So I can make an anti-Helmholtz magnetic coil pair, and I can use it to magnetically trap atoms. Okay. I can also trap atoms optically. Right? And this part is really important for doing the last step that gets us to a degenerate quantum gas. So using off-resonant light, there's an optical potential that looks like the dipole matrix element, so little electric dipole dotted into the electric field. This is a potential then that's proportional to the intensity of the waves of light. Okay, and so I can make these optical traps that look like this, and I realize them by putting my electric dipoles, my effective electric dipoles, which are the atoms, into a focused Gaussian laser. So all of the trapping and cooling we do is some combination of applying fields with magnetic fields with current carrying coils, or either focused or not particularly focused laser beams. And I mentioned that evaporative cooling is the last bit of the process. This is how we really get to the degenerate quantum gas. So for example, how we make a Bose-Einstein condensate. And so one of the last steps you do before you get to the actual science is you have a cold thermal cloud, right? So maybe it's 10 microkelvin or so, cloud of atoms, and you trap them in some intense optical field from a focused laser beam, and then you slowly rack down the power. That's equivalent to having atoms in a bowl shape like this, and I lower the power, and so that lowers the walls, and the hottest atoms will leave the trap. You allow the atoms to thermalize a little bit, and what you have left is you have a cloud with less atoms, but it is cold. Okay, and again, this is similar to how coffee, for example, evaporatively cools. And so here are some images of this process happening in a real experiment. I actually meant to put the credit from the Zerlines group. This is also a picture from Zerlines group. I have two cases, right? I can have a classical gas of bosons. For me, that will be lithium-7, or a classical gas, or a classical gas of fermions. For me, that will be lithium-6. We have both in the experiment. Okay. And so when the temperature is high, that is, temperature is this way to the right, temperature is high, everything's classical, the behavior of the bosons with fermions in a harmonic trap, they are similar. Okay. And so you have these images here showing the bosons on the top, fermions on the bottom. But as you cool the bosons and fermions down, beneath a transition temperature, something fundamentally very different happens. And that is because of the effect of Pauli exclusion, right? So fermions have to obey Pauli exclusion. So when you make them really cold, they don't have the liberty to just overlap with each other the way bosons. The fact that bosons don't have Pauli exclusion and overlap, they allow them to crowd up. And this gives you a Bose-Einstein condensate, right? So on the top row, we're cooling from thermal Bose gas, right? You go past the transition temperature, and now you have a Bose-Einstein condensate, sort of macroscopic occupation below its energy level. However, for fermions, the bottom row, even when you go below the transition temperature, you don't see visually a striking difference. And that's because due to Pauli exclusion, the fermions have to stack themselves up across the different energy levels of the trap. Okay, so here, these are my bosons. They have some de Broglie wavelength, which is something like the size of living spheres, but they can overlap. However, in my trapped fermion case, the de Broglie wavelength is roughly the size of this atom, but then the separation between the atoms are roughly the de Broglie wavelength. So they stack more like this. Okay. And so in the experiment that we're building, we're going to have both bosons and fermions. Right? Fermions are naturally more suited to do many body physics. We want to do single body physics, which I promise there's lots of interesting single body, single particle physics in the quasicrystal. then it's useful to have a Bose-Einstein condensate to do that. So that's what we're going to start with first. Bose-Einstein condensate of lithium-7 in a quasicrystal potential. Okay, so I just mentioned quasicrystal potential. What I really mean is a quasicrystalline optical lattice potential, or quasicrystalline optical lattice. Okay, but what do I mean by optical lattice? Well, mathematically, I can learn something from these waves and how they sum. I have a red and blue traveling wave. They're counterpropagating. They add to make the black wave. Okay, experimentally, I can realize this with two counterpropagating lasers. Lasers are just, in a sense, traveling waves of electric field. And if I look at the region where they overlap, and I look at the time average electric field intensity, that's what the atoms see, okay? I get a perfectly spaced 1D array, my 1D system of two counterpropagating lasers, that is spaced by half of the laser wave, okay? And I can throw atoms in there. Now I have a one-dimensional optical lattice potential, or one-dimensional optical lattice. It turns out we can use multiple pairs of intersecting beams to make either two-dimensional or three-dimensional lattices. These are periodic lattices that I'm talking about. Or we can use lasers to make quasi-periodic lattices that have a different set of symmetries. Okay. So I just mentioned for this 1D case, two traveling waves give me a standing wave where the optical potential is proportional to the laser intensity. This is my one-dimensional optical lattice. Okay. Now we want to move towards doing quantum simulation of solid materials, so solid crystals, right? And solid crystals are amazing. I'm very interested in the physics of solid crystals. But I would say that using atomic physics tools, we can learn a different set of things about solid crystals, given the sort of benefits that we have using modern AMO techniques, modern atomic physics techniques. Okay, so while solid crystals are incredible and beautiful in many ways, they are imperfect, right? We just learned in the talk before that solids, for example, have impurities. Sometimes those impurities are incredibly useful. Sometimes they're not. To be able to control them is a really nice thing, right? Solid crystals have fixed geometry. They have this angstrom level spacing, and so very fast dynamics. It's hard to measure dynamics of electrons in crystals for that reason. Whereas optical lattice, they are defect-free. They are adjustable. They have micron spacing and so much slower dynamics that we can image directly. And our electronics are fast enough to measure these things. Okay? So you have a bunch of imperfections, for example, in solid crystals that you just don't have in an optical lattice, which makes this an effective toy model for doing quantum simulation of some interesting material where the physics that you care about is not associated with the defects. And so it benefits you to remove those defects. Okay? You can have what are called interstitial atoms. So this is an extra atom that's in the regular lattice. So the regular lattice is these, the blue atoms here. Okay? You can have an extra atom that doesn't belong. You can have one of the blue atoms that has been substituted with a different atom. So it's in the regular array. It's just one of the atoms is different than the others. You can have a vacancy. Okay? You're missing one of the regular atoms. One of your regular atoms can be a different atom that's smaller than the rest of the regular array. You can have this sort of funny pair thing where you have a coupled vacancy and extra atom that are inserted into this regular array in a way that sort of locally like messes up the ordering of atoms. So all different kinds of imperfections you have in a solid state system, we don't have here, okay? And so as has been done for many years now, you can make 1D optical lattices or two-dimensional or three-dimensional optical lattices. Okay, so what is a crystal? This has become a really important question to me, and learning about what is a crystal and a little bit of stuff about group theory, I've learned that quasicrystals are quite interesting, okay? So what do crystals have? They have long range order. If you do a diffraction experiment, say I take a solid crystal, now I illuminate it with a beam of electrons or neutrons or X-rays, then and I look at the far field, I'll see a diffraction pattern with sharp peaks that come from a collection of different amounts of constructive and destructive interference, depending exactly where I'm looking in the far field. Okay? That's how people tell if things are a crystal. This is what crystallographers do to learn about materials. Okay? Crystals have band structure. I mentioned that if you're studying crystal physics, what you're really doing, and it doesn't matter if you're talking about matter waves propagating in a background potential, that can be charged matter waves, so electrons propagating around a background of ions, ultra-cold atom matter waves propagating in an optical potential, sound waves in a crystal, or sort of photonic crystals where light waves are propagating. All of this is the same thing over and over again. It is the details of waves propagating in a background potential, okay? And the details of what the frequencies of those waves can be, right? That is the band structure. Sometimes, depending on the details of the background potential, the wave can only have certain frequencies or energies. And if that wave doesn't have that frequency or energy, it cannot propagate. Like it physically cannot propagate through the system. Okay, that's what the band structure is. And so that tells you about things like transport properties. In a solid material, that is how do electrons flow through a solid material. Okay. Here I have a quick picture of band structure. This is a plot that I generated for a rubidium BEC. So just imagine a single rubidium atom in a hexagon lattice, actually. Right? The band structure shows that I have these different energy bands: the green, the blue, the pink, the purple, the orange, etc. And the ultra-cold atom, the matter wave, can only have energies, that's the vertical axis, that have particular values as a function of the momentum in the lattice. That's the horizontal axis, right? So the particles cannot have an energy that is in the white region, only in the colorful regions. And so the details of this structure can lead to some interesting physics. For example, I have this point labeled K. If you were talking about graphene, this point labeled K is called the Dirac point. And the Dirac point in graphene is incredibly interesting. The Dirac point in graphene, it makes electrons near it sort of look like relativistic particles. Okay, this is attached to the integer and the half integer quantum Hall effect, which is unique in graphene that you see both. This is unusual. Other fancy physical effects like ion tunneling, sort of a resonant tunneling effect. Also, the fact that the Dirac point, it sort of looks like magnetic monopole physics. And so associated with that, you have what's called variflux. This is the comment for the experts in the room. You have what looks like variflux that's confined to the Dirac points. And it's such that if you loop around that direction, your quantum system picks up exactly the pi vary phase, regardless of how large the loop is. Something interesting also happened like that at this other point called the quadratic band touching point, which I actually worked on with Zeppi in the audience when I was still a postdoc. And we use this technique using cold atoms to study how matter waves propagate in a way that, as far as I can tell, you cannot do in the solid state. And so this allowed us to do some initial measurements of what you could effectively think of as a quadratic version of the Dirac. Okay, so that's enough about crystals. What I wanted to get at for the moment is that they have long range order. You would see sharp diffraction peaks if you do a diffraction experiment, and they have band structure. This tells you about how the waves propagate through the system. Okay, so for a periodic lattice or a periodic crystal, there's something important called the crystallographic restriction theorem. Okay, this points to effectively a collection of allowed symmetries. Okay, and I wanted to point out this real physical crystal, real periodic crystal. Now the crystallographic restriction theorem leads to the fact that periodic lattices, they have to have translation symmetry, they have discrete translation symmetry, and they can only have a small set of rotation symmetries. So they can only be 2, 3, 4, 6-fold rotation symmetry. And that leads to real physical effects like this real crystal that has this cubic structure when it grows, right? That rotation symmetry has a real effect. It affects how facets grow when you grow a solid material. Okay. And so let me actually dig into this because this will show you a really important point about how quasicrystals are strikingly different than crystals. That is, given that a quasicrystal is also known as an aperiodic crystal, an aperiodic crystal is strikingly different than a periodic crystal because of the set of symmetries that describe it. Okay, so Here I have a periodic lattice. It's a square lattice. There's this concept of lattice vectors. It's sort of the smallest vector that allows you to define the spacing between all the atoms. And you can use two lattice vectors here to generate or span this entire square lattice. Okay, those lattice vectors are here. And so I can take sort of arbitrary combinations of these things and generate all the points, like I said. There we go. Okay, and as I mentioned, you can only have 2, 3, 4, 6-fold rotation symmetry. The square lattice has 4-fold rotation symmetry. That is, if you divide it, or if you rotate it by 360 degrees divided by 4, you get the same lattice. Okay, so that is me rotating from here to here. It's the same lattice. Okay, and so I can keep on doing all these additions. I recover the same lattice. Okay, this is really just to belabor that point. Spare that detail. Okay, so now let's look at a system that has 5-fold rotation symmetry. The question to ask yourself is this system compatible with translation symmetry? Okay, so here's my 5-fold rotation symmetric pattern. I'll just call it a pattern. Okay, I can do things like rotate it and see if it looks the same. Right? See if I can define lattice vectors that give me a copy or allows me to generate this 5-fold rotation symmetric lattice. Okay, so of course I can define lattice vectors using the spacing between the innermost pentagon that I have in my 5-fold symmetric pattern. That's fine. Okay. Now, oh, this is out of order. Interesting. Okay, sorry about that. Let me step back a little bit. I misordered some of these slides. Instead, let me think of my lattice vectors being generated by the distance from the central point out to the first pentagon. And I want to ask the question, if I add linear combinations of these like I did for the square lattice, does it give me the other point? Does it allow me to generate this whole lattice? Okay. And so I'll take 2 of those lattice vectors, I'll add them together, right? The resultant vector should give me a different point on the lattice, but it doesn't, right? I keep on doing this, and I find that I get a new pentagon at a smaller scale. It turns out that that scale is smaller by the golden ratio, 1.1 plus the square root of 5 all over 2. This is really interesting for lots of reasons that are not physics, but know that it's true, and this number, the golden ratio, appears in our system sort of everywhere that it can. Okay, but this central pentagon is smaller than this one by a factor of the golden ratio. Okay, and so then what are my lattice vectors? I can actually keep on adding combinations of the same lattice vectors, and I can get bigger or smaller pentagons. But if I just take the new pentagon and I define new lattice vectors, I do this process again, I get a smaller pentagon by the size, by a factor of the golden ratio. Okay. So you can do this ad infinitum, and you find that it is specifically the 5-fold rotation symmetric nature of this that leads to this not jiving with translation symmetry. Okay. Enough of that. Okay. So like I said, is rotation symmetry compatible with translation symmetry? The answer is yes, depending on which kind of rotation symmetry you're talking about. For 2, 3, 4, and 6-fold, the answer is yes. For 5, 7, 8, 9, 10, 11-fold, etc., the answer is no. And so another technical point for the experts, which I think is very interesting, these symmetries, along with translation symmetries and rotoreflection, blah, 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 inversion symmetry, blah, 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 this all falls into in a group theory language, the symmorphic space group. Okay. Symmorphic space group is very interesting. That describes all of your periodic lattices. But there are non-symmorphic real materials actually that have this additional set of symmetries. For any condensed matter people here, like Bly or screw symmetry, that leads to the wave function of electrons picking up an interesting sort of helical phase between different layers that build up the material. Okay? That is not part of the symmorphic space group, and there are no cold atom experiments that are looking at this, and I'm not even sure if you can generate an optical potential or not to do this, but I think this would be super interesting. And for my previous work, looking at sort of details in structure, in band structure. The symmetric space group crystals, so hexagon lattice, square lattice, all these things, triangle lattice, you can only ever have an interesting touching that's twofold. But if you want to have a larger degree of band touching points, you need to have a non-symmetric lattice. And so you can go from having your band structure basically give you a two-level system, right? If you're looking at physics around the intersection between two bands, this maps onto a two-level system. But if you want to use generally like a spin one model, then you would need more band touching. And the way to do that, I believe, is to go to a non-symmetric lattice. Okay. There's this model that's interesting called the SSL model, for example. Good. Okay, so I know I've belabored these things a lot, but this is pretty important. Let me just check the time. Good. I mentioned that if you're a crystallographer and you want to learn about some details of material, you would do diffraction. So let's say you're going to do electron diffraction. The electrons have some de Broglie wavelength lambda. You have some spacing between the atoms in the crystal that you want to study D. And if the Bragg law is satisfied, this constructive interference condition that some integer times the electron wavelength is equal to twice the distance between the layers of the material times sine of this angle of approach, then sort of depending on the details, depending on the incident angle, you can have constructive interference in the far field, or you can have destructive interference in the far field. And so what crystallographers do is they look at two-dimensional maps of this, and these maps should show you the symmetry for one directly, right? So if I look at this diffraction graph and I see that it's fourfold rotation-symmetric, that tells me automatically that I have a square lattice, right? And there's some other details about that, but it tells you that you have a square lattice, or if I see threefold symmetric, then there's like a family of lattices that might be. Okay, but one way to study something really important about your system is to do diffraction. Okay, and I can sort of say more about this, but I want to skip right to the sort of meat. Doing actual diffraction experiments back in the 80s, someone stumbled onto a diffraction pattern that people at the time thought could not exist. Okay, so Dan Shechtman did this diffraction experiment on an aluminum manganese alloy and measured this pattern. Okay, it has sharp peaks, but it violates the crystallographic restriction theorem because it has a rotation symmetry that's both 5 and 10-fold rotation symmetry. Okay, so this was shocking at the time, and basically many people, including the great Linus Pauling, the two-time chemistry laureate, tried to run him out of science. Right? There's this popular saying from Linus Pauling, like, there are no quasicrystals, only quasi-scientists. Right? So people did not like Dan Shechtman just because they were really trapped in dogma, but this was real. Okay, and after lots of scrutiny, Dan Shechtman's work actually led to the International Crystallographers Union to redefine what is a crystal. And so now aperiodic crystal, that is a real term. An aperiodic crystal is what Dan Shechtman found. This is what is known as a quasicrystal, as opposed to a periodic crystal. Okay. I mentioned this led to the Nobel Prize in 2011. Here's an image actually of a real quasicrystalline material. This is basically an SEM image of that. Solid state quasicrystals can exist in nature. They are rare. You only see them around high energy events like meteor strikes or old nuclear blast sites. So without that kind of external force, you don't naturally see them. Okay? But they do exist. Here's an electron microscope image of one of those. Okay, and so this, to me, as someone who builds atomic physics experiments, is incredibly interesting. Why is that? So I showed you band structure of a periodic crystal earlier, which I can calculate because I have the Schrodinger equation and I have Bloch's theorem, which tells me something that must be true about the wave function and its periodic boundary conditions in a periodic crystal. That's because of the translation. So for a periodic lattice, one of the main analytical or theoretical tools that you have is a particular solution to the Schrodinger equation. Okay, that allows you to derive a band structure and learn all these sort of important things. Okay, But quasicrystals, they do not have translation symmetry, so there's no blocks there. There's no nice solution that you can plug into the Schrodinger equation and define some set of equations that give you band structure. It's not a thing at all. Okay? And so what you have to do is either do very costly numerical experiments using high performance computing, or you're like me and Ulrich Schneider. I'm going to show some interesting work from his group where you build your quasicrystal and you do the experiments. Because to do anything from first principles is incredibly hard. Okay. And this is this point here, the lack of translational invariance, translational symmetry, it makes most of the things you want to do with quasicrystals theoretically intractable. And that's because you don't have block wave function solutions to the Schrodinger equation. Okay. And quasicrystals, they are non-periodic, but they do have long range order. There's what's called a deflation or inflation symmetry. And for us, it's set by the golden ratio. Good. So I'm going to get into a bit more about what we're doing at Yale. Here's a very nice picture of my university. Here's a 3D model of my vacuum chamber. It's a rather compact system. We've actually built all of this and it's wrapped up, except we don't have this object here. This is a very fancy glass cell. We're actually hoping to swap on that glass cell next week and sort of have a completed vacuum system. But like I said, it's very compact. There's an oven with lithium 6 and 7 down here. We make a vapor of this atom, these atoms, which go into a 2-dimensional magneto-optical trap. And this makes a beam of atoms. This is like the water coming out of a hose that I mentioned. In the span of not very many centimeters, it goes right into a 3D model. We collect the cold gas. Then we'll do optical transport. So we'll grab that cloud of atoms with a tightly focused beam, and we'll pull it into the sign cell, and then we'll make our quasicrystal potential and study the atoms inside the potential. Okay. So how are we going to do that? Well, you take 5 laser beams and you overlap them in a plane. Right. So my lattice plane, it is the plane of the screen, and I take 5 laser beams with the relative rotation of 2 pi over 5, so 72 degrees. And I look at the time average electric field intensity that I told you about earlier. That generates a potential for the atoms that looks like this. Right? I feel like, this is rather confusing to look at, right? You don't see any regular array, right? But if you look for long enough, you can, mentally rotate and see that it's 5 and 10-fold rotation symmetric. Okay. So interestingly, we take periodic waves and we force a quasicrystal by forcing a rotation symmetry that is non-crystallographic. We automatically get a quasicrystal. And so what are we going to do with this quasicrystal? We're going to put cold atoms in it, right? And we're going to study how the atoms propagate. Eventually, we want to know how fermions differ than bosons because we want to learn about many-body physics rather than single particle physics. Okay. But generally, we want to observe quantum phenomena that's been difficult to observe in solid state, and mostly that has been hard to predict because of this issue with the lack of translational invariance. Okay, and so the first thing we're going to do is a proof of principle to see that we do have that quasicrystal potential with via a diffraction experiment, just like a crystallographer would do. Okay, and so people typically refer to this as Kapitza-Dirac scattering. Here is the potential that I'm making with my 5 laser beams. Okay, and so there's this 2-photon scattering from this potential. Okay. The momentum transfer comes from the h bar k difference momentum that you get from different pairs of the 5 laser beams that make up the potential. Okay, and so let me sort of dig into that point a little bit here. 5 beams make my potential. Any pair of 2 beams, you can look at the nearest neighbors or the next nearest neighbors. They all make 1-dimensional optical lattices, right? So in effect, what I'm actually doing is making 10 1D optical lattices that are rotated relative to each other by 2 pi over 10. And I'm just overlapping these lattices with each other. Good. So all of those 10 1D lattices together, they actually give you a combination of what I would call lattice vectors at least in the momentum space. This is a sort of rather technical thing. Okay, and that pair of lattice vectors are actually degenerate is not the right word to say. They're redundant in a way. Okay, so you get two sets of lattice vectors that allow you to describe how the momentum of atoms that propagate in this quasicrystal potential can sort of evolve. There's this inner set of 10 lattice vectors, and there's this larger set. The magnitude of these two sets, they differ by just the golden ratio, but you actually don't need both of these. You can use either one of these sets, and you can, for example, generate the reciprocal space, the momentum space picture of a quasicrystal, which is just the Fourier transform of like the real like sort of lab frame potential. Okay. And so I mentioned that the lengths are separated by the golden ratio. That's good. Here's a plot actually from this really old theory paper that hasn't been experimentally investigated yet, that I find extremely interesting, where they calculate the ground state wave function of Bose-Einstein condensate in a potential like one I described for you. And so you can imagine that all of this compared to the rack scatter that I mentioned, that come from the light field exchanging into with the particles, they would allow you to undergo some random walk. So all these different points here, these are different momentum components of your atoms. And so the scattering events will random walk you around all these different points, okay? And so such an experiment has been done with a different kind of quasicrystal. So Ulrich Schneider's group at Cambridge, University of Cambridge, has an 8-fold quasicrystal. And they've been studying, for example, interesting like localization physics. There's some open questions about how localization, delocalization works in a quasicrystalline potential. They start with the Bose-Einstein condensate, and they flash on their 8-fold rotation-symmetric quasicrystalline potential, and they see all these octagons. This is a non-crystallographic rotation symmetry, and so they know they have a quasicrystal. And maybe just sort of interesting point that highlights the difference between Ulrich's system and mine. There are tilings. This is actually an old math concept that Penrose and Bruin and other people worked on for a long time. People wanted to make aperiodic tilings, right? So if you wanted to cover up some arbitrarily large area completely with an aperiodic tiling, could you do it? People figured this out. There's something called Penrose tiling, which is 5-fold rotation symmetric. That's related to my lattice. The potential that I showed you, it's actually, for anyone who knows what the Penrose tiling is, it seems to me, and I haven't been able to prove this mathematically yet, but it's a bunch of copies of the Penrose tiling that are stretched and compressed by the golden ratio and rotated by 2π/10. Actually, if you just take 3 copies of the Penrose tiling, you generate something like 95% of my potential or so. So it's an interesting connection to the Penrose tiling. It's not the Penrose tiling itself, but it's copies of it. Ulrich's system is based off of what's called the Amon-Buechner tiling. Another thing that's really interesting that might lead to some future physics, Ulrich's system can be viewed as a projection of a 4-dimensional cubic lattice on 2 dimensions. Mine is a 5-dimensional cubic lattice in 2 dimensions. I realize this is a wacky thing to say, but Penrose and other people also showed that these 2-dimensional tilings or quasicrystals, they can be generated from large or high-dimensional cubic lattices on 2 dimensions. Okay, so maybe there's some interesting connection to the physics of higher dimensions in the future. So, we're building our experiment up right now. There are a number of things we want to do. We haven't done them yet, but I want to show you about some of the stuff we want to do, or tell you about some of the stuff we want to do. So what are we going to do first? We will create our BEC in a harmonic trap using the steps that I told you about. This is my BEC. This is almost my BEC. This is my thermal gas that I'm evaporatively cooling to BEC. Now I have a BEC. Okay, I'll wrap on the lattice for some amount of time. Then I'll ramp it off. I turn on some harmonic trap for a very particular amount of time. This is a detail that I don't need to rely on, but for the experts, this is momentum space or matter wave focusing. Right? This will give us a momentum space image of our atoms. And then we will take an absorption where we sort of shine light from the top down and collect the shadow of the camera. Okay. And hopefully what we see then is a 5 and 10-fold rotation-symmetric picture of the momentum space components of the atom from having done all of these Kapitza-Dirac scatterings, all this momentum exchange with the optical field. Okay. Now I mentioned band structure in a periodic lattice. Okay, this is really important for periodic lattices. It's interesting to think about what that even means in a quasicrystal. Right, band structure, it comes from a particular solution to the Schrodinger equation, which necessarily relies on translations. So you might think, like, oh, okay, well, if I don't have translation symmetry, maybe I don't have band structure. That's not quite the right way to think about it, but certainly the energy spectrum of particles in a quasicrystal is, I would say, complex relative to that of the spectrum in a periodic lattice. Okay, so again, band structure. This is the energy as a function of momentum in the lattice. It tells you about how waves of different momenta can propagate through the lattice. Determines transport properties. You can see things like band gaps that may have some interesting topology at play. Okay, and this can lead to some topology that lends itself to being due to the band gaps themselves or how the bands touch each other. Okay, these are things you want to study in periodic lattices. These are questions, band gaps and topology, that led to understanding these things, led to the theoretical understanding of the quantum Hall effect, for example. Okay, so we want to think about these things in the context of quasicrystals. Okay, so we're going to think about band structure. Now, in my previous work, I did some experiments where I was evolving the momenta of really a Bose-Einstein condensate, where you can think a single atom in a hexagonal lattice potential. Okay, so this is, I don't want to get caught up in the details of this image, but know that when I ramp on my lattice, this is the zero momentum point, and I go to this special point. This is a Dirac point, for example, from graphene. And I can do these kinds of experiments where I boost the momenta to some value that I can control to understand some details of the energy band structure. Okay, I want to do stuff like that with the quasicrystal. That's part of the initial goal. Okay, so I want to start at some momentum and I want to go over to some interesting point and see what happens. Okay, how will we do that in a quasicrystal? So this is where the meat of the first experiments come from. Each of the laser beams bears some traveling wave. Okay, and I can control the phase of that wave within a crystal optic modulator. Okay, so I have my 5 beams that make my quasicrystal, and I can control their phases. Now, if I do a very particular ramp of those phases, happens to look like this, details don't matter so much right now, then I can do something like have a fixed geometry quasicrystal potential and translate it. Okay, so I can translate my potential with the stationary BEC. I can throw my BEC in there. But this is the same, the fixed BEC moving with the background potential. This is the same as fixed potential with a BEC that is a coherent matter wave propagating through the potential. So this is the physics that I'm trying to understand. How does a matter wave propagate through a quasicrystalline background potential? Now there's some interesting work, some interesting theory work that's been done on a lattice that's similar to mine. It's just 5-fold symmetric. It doesn't have a 10-fold like mine does. But playing some tricks with adiopaticity, okay, you can actually recover what looks like traditional band structure of a periodic lattice. Right? This is a really strange thing. Okay, so periodic lattices with translation symmetry, they give you well-defined bands, with sometimes well-defined gaps or well-defined band touching points. Okay. The gaps, for example, can appear at the edges of the Brillouin zone. This is a rather technical point. And it's because there are plus or minus momentum pairs that would be degenerate, but they're coupled, and so they open up a gap. This is sort of normal avoided crossing type physics. Right? In a quasicrystal, It's not just plus or minus momentum, so I'm gonna call this K, plus or minus K pairs. It's really plus or minus time reversal symmetric pairs, right? And you can have sort of arbitrary plus or minus time reversal symmetric pairs, sort of at all momentum. So I think one way to think of a quasicrystal band structure is you in a general case, like you take the band structure of a periodic lattice, and if I was like to perturbatively turn on quasicrystalline symmetry, I would open up, like basically I would bifurcate the band sort of everywhere. And this is actually really interesting. This leads to fractality in the band structure. So quasicrystals are thought to also have fractal band structures. Maybe that leads to some properties that are specific to like fractals appearing in the spectrum that defines how like the energy of waves propagating through a quasicrystal potential. Okay, so I mentioned this bifurcation that leads to this like really messy fractal band structure. If you play with adiabaticity, you can adiabatically eliminate lots of those bands and recover what looks like well-separated energy bands with a effective Brillouin zone. So in, for example, my quasicrystal system, this will be a Brillouin zone that is tenfold rotation-symmetric. Okay? There's a Brillouin zone edge. There are interesting points where bands might touch. And so you can imagine doing an experiment where I take a condensate and I evolve its momentum, starting from zero momentum out to the edge of the Brillouin zone. I just keep on going. Right? What would I see? Well, if I really have nicely defined energy bands where the slope is positive here and I cross the edge of the Brillouin zone and the slope changes sign, well, the group velocity cares about the slope. It is the slope of this energy band. So I'll have a system where the group velocity changes. And this is Bloch oscillations, which to atomic physics credit was first measured in the atomic physics system. Right? People in solid state can measure it now. This is a relatively new thing for solid state people. And of course, this is something that you typically think of as being an effect from translation symmetry, from periodic crystals. But I'm telling you that there's a regime in which you would have Bloch oscillations in quasicrystals. This would be very interesting, I think. Okay? So this is one of the first things we hope to look at. Okay, so for people who are worried about phase stabilization, you're right, this is incredibly important. If you don't do a good job of phase stabilizing your beams, this is what your lattice looks like. And you can look at this forever and try to think of what's happening. And I don't think you can, I can't make any sense of this. And that's because the lattice points are sort of, they look like they're sort of, maybe they're rotating around, they're kind of splashing in and out of existence. This is sort of a weird thing. So I expect that if you don't do a good job of phase stabilizing your beams, you get sort of uncontrolled heating for the kinds of experiments that we want to do. For people who are familiar with Ulrich's group and their work, the localization physics that they are doing, it doesn't care about this. They can look at sort of like each experimental shot, they get technically a different looking quasicrystal potential, has the same symmetries, but it does look different. But it doesn't matter. For us, like I really want a effectively static quasicrystal potential with a moving wave, and so I have to phase stabilize my beams. Another sort of interesting mathematical thing, I'm almost done by the way, I know you can talk for a while, that I found myself looking into is how do I relate this to the higher dimensional space? I mentioned that my quasicrystal potential, it is a particular projection of a 5-dimensional cubic lattice onto 2 dimensions. And so what I want to understand is, like for every, I don't know, delta theta of phase from one of my in the electric field of one of my laser beams, what does that mean about the projection? Like if I imagine I have some fixed projection window in 5-dimensional space, if I change theta of one of my beams, am I translating my 5D cubic lattice? Am I rotating it? Am I doing a combination of that? Actually, I started a collaboration with a math professor who is interested in this stuff. And so we're trying to figure this out. So I mean, I can talk to you later if you find that interesting, but I think this is a very, very interesting thing. I already actually sort of got ahead of myself and mentioned Bloch oscillations. I don't need to say anything more about this, just this is sort of one of the first things I want to study is band structure and Bloch oscillations because I've become very interested in just band structure in general. And I want to know, is there some topology at play in quasicrystals? Topology plays a really important role in the properties of periodic materials, right? I mentioned that It's really the interplay of topology, right, of an abstract space, but it's topology that leads to like the quantum polygon, for example. And so topology is hard to define in a quasicrystal. There have been some recent theory interests in what topology and quasicrystals mean. And I really want to do some experiments to sort of uncover the interplay of quantum mechanics and topology and quasicrystals. Okay, so that is everything for me. Again, we're making a two-dimensional quasicrystal. We'll do it with 5 beams. Here's the potential. It's 5 and 10-fold symmetric. We're going to start with Bose-Einstein condensates in that potential. But in the future, I want to put a degenerate Fermi gas in that potential, learn about many body physics there. And this does exist in real life. Here's a solid state electron microscopy image of this really incredible material that you only get around really energetically extreme events. And actually, for a long time, it was actually, I think this is still not understood. But why would a collection of atoms even form themselves? Why would they even freeze into an arrangement that's 5-fold rotation symmetric? This is somehow energetically favorable in some regime through which they cool, but this is actually a really weird thing that these exist at all. So yeah, we're going to be studying them soon. Thanks.
Okay, questions? Yeah.
Thanks. Super cool talk. Thanks. With 2 parts. The first one was just technical. Are the beams retroreflected when you're forming this lattice?
No.
They're not. I see. Okay.
So just continuous wave. They will all overlap at the center of the cell, and then we'll collect them and do stuff to them.
Okay. So then they're also coherent. I guess all the same frequency.
They are. Yep.
Okay. Got it. Cool.
Yeah. There are some interesting. Actually, one thing that I find interesting about this. I imagine first experiments there all be coherent. I can control them with my ALMs to make some of them coherent and some of them not. So I can, for example, break a 2-fold symmetry and make something that's 5-fold symmetric and not 10.
Yeah.
And so I'll have a nice handle on changing the symmetries in a drastic way. And I would like to see how the physics changes as I do that.
Got it. Cool. Okay. And then the other thing that is basically blowing my mind is that you said that the band structure is fractal for a quasicrystal.
This is what people think. Yep.
Okay. And then, but in practice, it's kind of smoothed out. Is that like due to the BEC size not being it? Is like finite size effect of the BEC, or why do you get something that looks like a smoothish band structure when it's supposed to be fractal looking?
Oh, yeah. So this will only be true for like dynamical experiments. So like depending on the details of how I like boost the condensate to some non-zero momentum and near the edge of the Brillouin zone in that regime, basically like my atoms might have some energy that's large or small relative to certain gaps. And so then that means that certain gaps either matter or they don't for the dynamics. So again, it's playing around with adiopaticity in a regime where you have to have a moving condensate. The condensate is stationary, then I just have this fractal band structure. And actually it limits my ability to study it.
Mm-hmm. So, okay, got it.
Yeah.
Really cool talk. I had a question about the when you're moving this lattice around the BEC.
Mm-hmm.
I guess it's kind of like a hardware implementation question, but if my understanding was the BEC is held by the lattice, so how do you keep the BEC fixed without disrupting the lattice or without,
Well, keep it fixed without disrupting the lattice.
like how is it held in place, I guess?
Yeah. So we can do things like have some additional external optical dipole traps, so just a focused beam to sort of hold the BEC there. The atoms are also like held by the optical field itself. And I can do things like gravity compensation with magnetic field gradient. So external potentials.
Okay. I'm gonna ask one question.
Yeah.
I know you've been here a long time, but one question. So, have you looked at Hubbard models in the quasicrystal, and are there qualitative versus quantitative differences?
Yes and yes. In the 8-fold quasicrystal, you can develop a Hubbard model because you can do this interesting analytical trick. So the eightfold quasicrystal you can generate via two square lattices that are rotated by 45 degrees. And you can define this parameter that is that's defined spatially across these two overlap square lattices. And basically what you end up doing is you have to label the two square lattices and you look at the distance of closest approach between like the nearest lattice points to each square lattice. And you say that that is a parameter. Using that parameter, you can define it. I can't tell if I can do that with this one because I can certainly tell you that my potential is not some rotated pair of square lattices. But you can do that, and the phase diagram does lead to some different phases. There's an interesting Bose-Glass phase. There's some weird things that look like a small change on charge density waves and different strike phases. So yeah, we can talk more about that later.
Yeah, no, that seems good. All right, well, thank you for your patience and thanks for
Hopefully